10.5 Absolute Convergence, the ratio and root tests. The outline of this video is as follows. We will begin by defining a concept called absolute convergence, which is a stronger type of convergence for infinite series. Then, we will introduce two powerful new tools for testing: a series for convergence, the ratio test, and the root test. We will state the theorems for each and discuss the conditions under which they can be applied. Finally, we will work through several examples to see how to use these tests in practice and to build our intuition for when each test is most effective. We will now explore a stronger type of convergence that is especially useful for series with both positive and negative terms. The main idea is to test for convergence without relying on any potential cancellation between positive and negative values. We do this by forcing every term to be positive by taking its absolute value. This leads to a formal definition. A series is said to converge absolutely, or be absolutely convergent, if the new series formed by taking the absolute value of each term converges. So, to test for absolute convergence, you simply create a related series of all non-negative terms and check if that one converges. For example, consider the geometric series shown, which is the sum from n equals 0 to infinity of 5 times the quantity negative 1/4 to the power n. If we take the absolute value of each term, we get the series which is the sum of 5 times positive 1/4 to the power n. This is a simple geometric series with a ratio of 1/4, which converges. Because the series of absolute values converges, we say the original series converges absolutely. The absolute convergence test is a powerful tool for series with mixed positive and negative terms. It let us prove convergence by looking at a related series that has only non-negative terms. The test states that if the series of the absolute values of the terms converges, then the original series also converges. The proof works by creating a new, non-negative series using the inequality shown. This new series is bounded by 2 times the series of absolute values, so it must converge by the direct comparison test. We then show that our original series can be written as the difference of two convergent series. Since the difference of two convergent series is always convergent, our original series must converge as well. Regarding the caution, please note that the theorem is correct. The intended point is that the converse is not true. A series can converge even if the series of its absolute values diverges. So the main takeaway is that absolute convergence is a stronger condition that guarantees regular convergence. Let us apply the absolute convergence test to see how it works in practice. This test is a powerful tool for series that contain both positive and negative terms. Our first example is an alternating series, the sum of -1 to the power of n plus 1, all over n squared. To test for absolute convergence, we create a new series by taking the absolute value of each term. This simply removes the alternating sign, leaving the sum of 1 over n squared. We should recognize this as a p-series, with p equal to 2. Since p is greater than 1, this series of absolute values converges. Therefore, the original alternating series converges absolutely, which implies that it converges. Our second example is the sum of sine of n over n squared. We again form the series of absolute values. Since the absolute value of sine of n is always less than or equal to 1, we can use the direct comparison test. Each term in our series of absolute values is less than or equal to the corresponding term in the convergent p-series, 1 over n squared. This means our series of absolute values must also converge. So, the original series converges absolutely, and thus it converges. The ratio test is a powerful tool for determining if a series converges, especially when its terms involve factorials or exponentials. This test works by measuring the rate of growth between consecutive terms. We calculate a value, rho, which is the limit as n approaches infinity of the absolute value of the fraction a sub n plus 1 over a sub n. The result of this limit tells us about the series' behavior. If rho is less than 1, the series converges absolutely. If rho is greater than 1 or is infinite, the series diverges. Crucially, if rho is exactly equal to 1, the test is inconclusive, and we must use a different test. The reason this works is that a rho value less than 1 implies that, eventually, the series terms are decreasing by a factor smaller than 1, behaving like a convergent geometric series. Therefore, the ratio test determines convergence by comparing the series' long-term behavior to a geometric series. The ratio test has a significant limitation. It is inconclusive when the limit of the ratio, which we call rho, is exactly equal to 1. This means the test fails to determine whether the series converges or diverges, and we must use a different method. To see why, let us examine two familiar series. First, consider the harmonic series, the sum of 1 over n. We already know from the integral test that this series diverges. However, if we apply the ratio test, we find that the limit of the ratio of consecutive terms is exactly 1. Next, consider the p-series with p equals 2, which is the sum of 1 over n squared. We know this series converges, but when we apply the ratio test to this series, the limit of the ratio is also 1. Since we found rho equals 1 for both a divergent series and a convergent one, the test cannot distinguish between them. Therefore, if you calculate the limit to be 1, the ratio test provides no information about convergence. Now let us apply the ratio test to a second example, which is a great illustration of how well this test works with series that contain factorials. The general term of our series, a sub n, is the quantity 2n factorial divided by the product of n factorial with itself. First, we construct the next term, a sub n plus 1, by replacing every n with the quantity n plus 1. Then, we form the ratio of a sub n plus 1 over a sub n. The key to simplifying this complex fraction is to expand the larger factorials. For example, factorial is equal to 2n plus 2 times 2n plus 1 times 2n factorial. Similarly, n plus 1 factorial is n plus 1 times n factorial. After canceling the common factorial terms from the numerator and denominator, we are left with the much simpler expression 4n plus 2 divided by n plus 1. As n approaches infinity, the limit of this ratio is 4. Since the limit, rho, is 4, which is greater than 1, we conclude from the ratio test that this series diverges. Here we have another powerful tool for determining convergence, called the root test. It is particularly useful when the terms of our series involve expressions raised to the nth power. The structure of this test is very similar to the ratio test. We begin by calculating a limit, which we call rho. Rho is the limit, as n approaches infinity, of the nth root of the absolute value of the term a sub n. The conclusion, then, depends entirely on this value. If rho is less than 1, the series converges absolutely. If rho is greater than 1, the series diverges. And, just as with the ratio test, if rho is exactly equal to 1, the test is inconclusive, and we must try another method. The reasoning for the convergence case is based on a comparison. If rho is less than 1, then for large values of n, the term a sub n is smaller than the corresponding term of a convergent geometric series. This comparison proves that our series must also converge. So the key takeaway is to use the root test when you see terms raised to the power of n, as taking the nth root often simplifies the expression dramatically. Let us look at an example that shows why the root test is a valuable tool, especially when the ratio test fails. Recall the series where the terms a sub n are defined piecewise. For this series, the ratio test was inconclusive, because the ratio of successive terms did not approach a single limit. However, the root test works very well here. We examine the nth root of the absolute value of a sub n. When n is even, this root is exactly 1/2. When n is odd, the root is the quantity, the nth root of n, all divided by 2. Now, we need to find the limit as n approaches infinity. A key limit to remember is that the nth root of n approaches 1. Therefore, for both the odd and even cases, our expression approaches the same value, 1/2. The limit rho is 1/2. Because 1/2 is less than 1, we can conclude from the root test that the series converges absolutely. Let us work through 3 more examples to see the root test in action. First, consider the series with terms n squared over 2 to the power of n. When we take the nth root, we get the nth root of n squared, all divided by 2. We know the limit of the nth root of n is 1. Therefore, our limit rho becomes 1 squared over 2, which is 1/2. Since rho is less than 1, the series converges. Next, we examine the series 2 to the power of n over n cubed. Applying the nth root, the numerator simplifies to 2, and the denominator becomes the nth root of n cubed. The limit of the denominator is 1 cubed, so rho is 2 over 1, which equals 2. Because this is greater than 1, the series diverges. Finally, we have a series where the denominator is raised to the nth power. The root test is perfect for this. The nth root cancels the nth power, leaving the simple limit of 1 over the quantity 1 plus n. As n approaches infinity, this fraction goes to 0. Since rho equals 0, which is less than 1, the series converges. Let us summarize the 2 powerful tools we have just learned for determining absolute convergence: the ratio test and the root test. Both tests rely on calculating a limit, which we call rho, and comparing its value to 1. First, the ratio test. Here, we find rho by taking the limit of the absolute value of the ratio of a term to its preceding term. If rho is less than 1, the series converges absolutely. If rho is greater than 1, the series diverges. If rho is exactly 1, the test is inconclusive, and we must try another method. This test is especially useful for series that involve factorials or terms raised to the nth power. Second, the root test. For this test, rho is the limit of the nth root of the absolute value of the nth term. The conclusions are identical to the ratio test: absolute convergence if rho is less than 1, divergence if rho is greater than 1, and inconclusive if rho equals 1. The root test is most effective when the terms of the series are themselves raised to the nth power. Let us review 2 important applications of the ratio test to see where it excels and where it fails. First, consider the series with terms -10 to the n divided by n factorial. This is a perfect case for the ratio test, because the factorial terms simplify cleanly. When we take the limit of the absolute value of the ratio of consecutive terms, it reduces to the limit of 10 over the quantity n plus 1. As n approaches infinity, this limit is 0. Because the result, rho, is 0, which is less than 1, the series converges absolutely. Now, let us examine why the ratio test is always inconclusive for p-series, which have the form 1 over n to the power of p. The ratio of consecutive terms simplifies to the fraction n over n plus 1, all raised to the power of p. As n approaches infinity, the fraction inside the parentheses approaches 1. And 1 raised to any power p is still 1. The limit is always 1, so the test provides no information. This shows that while the ratio test is powerful for series with factorials or exponentials, it cannot determine the convergence of p-series.